Thank you, everybody. Thank you for coming, this huge number, to our presentation. In this talk, we are going to talk about practical demystification of CRDT. I'm Nami, he's Dmitry, and Didier, who had great contribution but couldn't join us. So first disclaimer is that we are not hardcore academic guys. We are not that much expert in the distributed system. We won't just use some achievement from the academic in our, to solve our real-world problems. We are full stack developers, so we are doing many things. We are doing backend, front-end, infrastructure. While I'm talking to you, I'm also on call for my backend service, so if something goes wrong, I have to react fast. And we are working in TomTom, and we are working on a system called NavCloud, which is a cloud-based storage service to let users synchronize their navigation information. TomTom has a lot of clients in the market, a lot of devices, a lot of automotive have contract with TomTom, so most of them are gradually will integrate with NavCloud, and already many of them had. So NavCloud should handle a lot of requests, so NavCloud should be scalable and available. And because location-based information is one of the most sensitive information, NavCloud should be really secure and also should comply with the legal requirements. And also NavCloud wanted to be used in a third-party application and TomTom application as well, so we should not degrade their performance, should we have to be reactive and respond quite fast. We try to use a technology that matches our requirements very well, so in the server we use Scala as a core language and also Spray and Akka on top of that, using RabbitMQ for push notification, React for our storage, and we deploy in Amazon. And also, to facilitate integration with NavCloud, we implement different SDKs in a different abstraction level with a different technology, Android, Java, C++, etc., etc. Many synchronization systems and also NavCloud have specific characteristics, especially NavCloud, which is used in navigation devices, and most of them have SIM card built in. And this SIM card will be paid by the company, by TomTom or by automotive company. So they have very low bandwidth, and although also when you're driving, most of the time you're in places that you don't have internet, because, for example, you go to the farm, doesn't have any coverage, you're going to the tunnel, you're parking in the parking, so you don't have internet. So the characteristic is that the connection is unstable, as I said, bandwidth is limited, and user doesn't want to wait until he gets the internet and apply updates on his information. He wants to seamlessly just change things. And of course, because the duration of this connection is big, you may change concurrently, and these changes may be in conflicting state. And of course, order is not guaranteed. If I change something now, it may reach server an hour later, okay, and some other changes can happen meanwhile. And of course, user cannot accept the data is going to be lost, and this is against the legal requirement. And of course, data should be convergent to the value that user most probably expect. So how to deal with that? You can first write a lot of logic, trying to cover all the corner cases, a lot of code effort to handle everything. I doubt that is even possible, but if it's possible, it brings you a very unmaintainable code. And as Linus Torvalds said, the good developer always focus on the data structure. They want to solve the problem at the data structure level, so they want to gain benefits out of the box. This is the reason that we went for CRDT. So we said we wanted to try CRDT. As I said, CRDT is a data type, it's a data structure, and it has its own it's a family, a little bit ambiguous, but it's a range of data structures. And it has its own algebra. And also it's replicated, so it's meant to be distributed. So at any time, any instance of CRDT can have multiple replica, which these replica can be out of sync. And can be out of sync is one thing, and they can be even in a conflicting state. Most of you work with these source control tools like Git. Sometimes Git solves the conflicts for you using something like recursive strategy, but sometimes it cannot, and you have to interfere. So user should interfere. But CRDT says no user interfere. I know what I have to do. How does it do that? The main ingredient of these lot of benefits is something called merge. Merge is a part of the CRDT algebra. What is merge? Merge is a binary operation on two CRDTs having these characteristics. So merge must be commutative, must be associative, and must be idempotent. And it's really clear what those are. So why CRDT should have these characteristics? What does it bring for us? Apparently, these characteristics matches really well with the distributed nature. In distributed systems, order is not guaranteed. So you may send events, I may send event to you, but a couple of events to you, but there is no guarantee that in which order you receive those. Imagine that I'm a server, I receive your events, and I have a local state. I just merged to the local state, merged to the local state, merged to the local state. But my merge is commutative and associative. So no matter in which order that I receive those, they all will converge to the same value. So apparently really good for the distributed system. Another thing is that in distributed systems, events can be delivered more than once. So I send you an event, you send me back an ACK. ACK may be lost. I thought that you haven't received it. I resend it to you. But you received it twice. But again, you just merge it to the current state, and you get it multiple times. But because merge is idempotent, doesn't matter. It reaches a same value. And what does it bring in practice is that you can change things locally. You don't need any on-demand remote synchronization. You can change things locally, and they will reach server at some point. And local changes, be able to apply changes in offline mode, actually brings a great user experience because user doesn't need to wait until it gets the internet. I explained some couple of very easy examples about CRDT. The first is GCounter. GCounter is always growing counter, so the counter that always grows. For example, you have a website and you want to count the number of the hits on your website. And probably your website is really successful and you cannot count it in just one single machine. So you want to distributedly count. Addition is not a very CRDT compliant operation because imagine I have different 3 machines and each of them can receive the request count. And if I have numbers in each of them and just increase them, I cannot merge them because addition is not idempotent. If I send an event and it receives twice, it counted wrongly. So I have to think about the data structure that suits well. So we define an array which has elements corresponding to each machine. So I have 3 machines here, A, B, C, and so I have array of 3 elements. This is exactly vector clock. So whenever A receives a request for count, it's just increased their corresponding elements. So A always incremented the first element. And at some intervals, they talk to each other, they gossip with each other to propagate, to broadcast this information to reach their state to the total state. And upon gossiping, for example, C receives the array from B and A, it just merged to its own array. How does it merge? It just picks the maximum of the corresponding element. So here, for example, if C receives from B and A, the result will be 639 because the maximum of each element will be this. And what will be the total value is sum of them. So in this way, I count. I distributed count, and it's going to work, and I never count twice. It never lies to me. It maybe shows something behind, but eventually will consistent to the correct value. Why does it work? Because I use max in the merging, and max is CRDT compliant. Max is associative, commutative, and idempotent. And this is why it works. Another example, even as a simpler example, is GSet. GSet is always growing set. You can just add element to the set. Adding element to set is actually union of a set of one element to another union. But union, unlike add, is compliant, CRDT compliant. So I don't need to change my data structure. I just have different set in different machine. Whenever they receive a value, they just change the local state. I said local update is the great benefit of NavCloud, of CRDTs. So whenever they're gossiping to each other, they just union them. And of course, union is CRDT compliant because union is associative, commutative, and idempotent. Okay, how this data structure will help us in NavCloud? NavCloud has different use cases. One of them is the synchronizing the favorite location. So you may go somewhere, you like it, you mark it as a favorite. And regardless which device that you use or whether you have a connection or not, you want this to propagate it seamlessly. And you want to have a list of the favorites regardless where you set them. Favorite has a different attributes like name, longitude, latitude, address, etc., etc. Naive approach is that just LastRightWins. Whatever server receives, it just writes it to the database. So this obviously is not going to work because imagine I'm offline and I send the data. For example, I'm in a parking. I don't have internet. I want to mark this parking because it's a nice parking and it's cheap as a favorite location, but I don't have an internet. So I click there and imagine that an hour later it will reach the server. But in meanwhile, I also may apply some other changes. So it will override my newer changes. And also, you can solve this by attaching timestamp, but which timestamp? There is no reliable clock of your device, clock of your server. You never know. Although, as Dmitry is going to explain you, we are going to use timestamp, but we are going to use a simpler version and a little bit tweaking around that. So the result will that the stale update will win. So you may have stale update will win the newer update. So let's try CRDT, because CRDT apparently is a good match for this environment. You already saw this slide. This is the nature of NavCloud. Unstable connection, fine. CRDT said that I don't need on-demand remote synchronization. I can't just change things locally. Low bandwidth. We extended the algebra of CRDT to support another operation called diff. So what does that mean? It means that whenever I want to send an update to the server, instead of sending the entire CRDT, I just send the difference between this local state and the last state that I have seen from the server. So I optimize the bandwidth. Seamless edit view, this is by nature. Concurrent changes, of course you can have conflicting changes, but CRDT says that I know how to solve it. No guarantee on update order, we don't care. CRDT is associative and commutative. Data loss, we never override, we always merge, so we're not gonna lose data. And data convergence to the expected value. Okay, why? Because we use this data structure everywhere. We use this data structure in client, we use this data structure in server, and even we use this data structure in the database. So no matter which technology that we use, we have CRDT set or CRDT whatever in the client, in the server, in the database, and all of them do them merging things. And the merge logic is consistent everywhere. For example, we are using Riak as our data store. Riak has a very nice feature which attaching vector clock to an entry that you enter is a key value-based database. So whenever you write something, Riak attach a vector clock. It's some kind of a little bit different from the pure vector clock concept. It's a kind of versioning things, but it's quite close. So it attach a vector clock to that. Whenever you read that value, you also read the vector clock. When you want to write back, you have to provide the last vector clock that you have seen. If the vector clock that you provide is actually the most up-to-date one, and it's exactly the same with the one in the database, your write will overwrite the previous one. But if your vector clock, meanwhile that you are reading, someone else changed something in the database, the vector clock of that entry will be changed. So when you write back, your write will be considered as a stale write. And in this case, if you configure Riak will keep both versions for you. And this is your application responsibility to up on read, resolve those conflicts. But for us, we don't care. It creates sibling for us, awesome. What we store in the database is CRDTs. We read the CRDTs and we just merge them. 2 lines of code, no logic. And we know that this merge will converge with all the clients and all the other I don't know, devices, iPad, iPhone, everything. So this is actually a little bit of theory, and now Dmitry is going to talk about the details of how we implement and how we actually extend the concept of the CRDT to match our needs.
Cool. Thanks, Nami. So yeah, once we were sort of sold to CRDT concept, we decided, okay, we need to do our homework. So we wanted to try to model favorites as CRDT set. And now we actually needed to see what are the existing implementations of CRDT sets and pick the one that fits our needs. So we already seen the GSet concept, but it only allows additions, not removals. For favorite locations, well, it's not the case. We have to support updating and removing of the elements. So we looked a little bit further. We looked at the two-phase set. So what is two-phase set? Two-phase set stores information about addition operations and removal operations. So removal is supported. And it can be implemented using basically just 2 GSets. In first GSet, we store our addition operations, and in the second one, removal operations. Really simple, right? So this is how it will look like in the example. So we have 2 nodes, A and B. Both have the addition and removal sets. So how do we do lookup? How do we get the total value of the set? Well, I guess it's pretty intuitive. We just need to count the diff between the add set and remove set. And these will be the elements which are not deleted yet. And how do we calculate the merge? So how do we merge two sets together? Well, we just need to take a union of add set and a union of remove set, and we construct the new value. So here is exactly what we do in here. So this is the result of the merge and of the lookup. I would argue it's pretty simple, right? And here's like a small implementation in Scala. We have the code for all the common CRDTs published. We will give you a link later. Although it didn't work for us, for two reasons. So one reason is that once the element has been removed from a two-phase set, well, it's removed forever, so you cannot re-add it back. The second thing is a little bit more even arguable. The elements are inherently immutable, so no updates is possible. Of course, with immutability, you can still model updates by just removing element and then adding again the changed value. Although it really easily brings much more tombstones or removed elements to the set. So the remove set grows really, really fast, especially on the hot elements that are updated too fast, which we wanted to avoid. So there are multiple, there are at least few sets that are trying to tackle problems of two-phase set. The first one is LastRightWins element set. So yeah, LastRightWins doesn't sound really promising, I would argue. So it also stores an addition and removal operations. Again, can be modeled as GSet. But as it's common in distributed systems practice, so if you want to get some additional features, for example, you have this spatial trade-off. You have to introduce some sort of additional metadata, like we do with Tomstones. So in the case of LastRightWins, it's actually timestamp, which is associated with every remove or addition operations. And yeah, each element has a timestamp. In that case, actually, we can re-add element to the set which has been removed by just creating an addition operation with the higher timestamp than the one that is stored in the remove set. So here's an example. Again, two machines. We have these pairs. The first element in the pair is actually a timestamp, just a long value and the value itself. So how do we calculate the lookup for the set? Well, we just need to analyze again the add set for the elements and their timestamps and check for if the element has a corresponding state in the remove set with the timestamp higher. And if it has, then, well, it's considered as removed one. It won't show up in the lookup. And for merging, the merging is exactly the same. We just need to take the union of add set and remove set. This is what we're doing here. And based on the merge result, we get this lookup. Pretty easy. Yeah, and that's how you can basically implement that, the basic operation lookup and merge. So as you see, merge is pretty the same for these sets. It didn't work for us, though, again. The main reason is still the elements are immutable, which means that the remove set will grow really fast, again. So it solved one problem of the two-phase set with re-adding elements. Doesn't solve still yet, the other one. So the next one is OR set. So OR set stands for observed and removed set. So again, it stores addition operations and remove operations. Can be stored separately into GSets again. So in the case of OR set, it actually uses the provides additional causality for additions and for removals. So when you add element to the OR set, you provide the unique tag, which is associated with the particular addition operation. If you want to remove element from the OR set, you have to find all the pairs in the add set, in the GSet, take all these tags and put these tags to the remove set, basically. And of course, it supports re-adding elements. You just create a new addition operation with new unique tag, which is not yet in the remove set. So based on that, we can imagine how the lookup function will look like for OR set. Yes, we basically need to again traverse the add set and find those elements that have tags which are not yet present in the remove set. And basically, that's what we're doing here. So the merge works, surprise, surprise, exactly the same. We just take a union of add set and remove set, and that's basically our merge. The lookup, yeah, that's how we calculated lookup in here. So we have also a code sample for the lookup operation, basically traversing the add set and then finding the corresponding elements in the remove set. Yeah, and merge is exactly the same. Again, it has the same problem, or yeah, for us it's still a problem, as a LWW and two-phase. The immutable elements, well, the element's still immutable, right? So then we started thinking, okay, can we enhance a little bit for our needs, the existing sets? So we said, okay, can we introduce our own set, our set? Yes, okay. And incidentally, we called it actually our set as updated, observed, updated, and remove set. So yeah, we use the same technique, kind of, by providing additional metadata that was basically helping to solve our needs. So first of all, we said, okay, we want to be able to mutate, to update the elements. We want to identify the elements. So we introduced this identifier, which is associated with each element. It's a unique identifier. We use UUIDs. The second thing that we said, okay, we also want to have timestamps to work the same way as in LastRightWins set, to be able to re-add elements and to solve the conflicting copies. And basically, that's the principle. So we have sort of identity of the element, which is immutable, right? So it's there forever once the element is generated. It has this non-changed ID, but the value is mutable. So we ended up with this structure. So the metadata that we added is basically ID, as I said, timestamp, and this funky remove flag. So why do we need that? Well, we could have modeled that one as a two separate sets for additions and removals. It's not a problem. We wanted to save some space, and we said, okay, if we introduce that discriminator field for marking the element as removed or non-removed, yeah, it's actually works pretty well. So yeah, and of course, set can contain only one element with particular ID. So here's an example. Again, two machines. So we have these four fields. So the UUID, timestamp, the value itself, and the optional remove flag, which if it's not set, then it's false. So how do we calculate the lookup for our set? So for example, on a machine, we just need to traverse the underlying sets of our set of our elements and find those which are not removed. It's pretty easy, right? How do we merge? So the merge in that case is a little bit more involved, not that much. So if we need to merge the values from two machines, we have to, well, take all the elements from both underlying sets, then we group them by ID. We get these subgroups for each element. These are like conflicting copies that has to be resolved. So we need to reduce across these groups. How do we reduce? Well, we have a timestamp. So we can say, okay, we pick the winner based on a timestamp, if it's possible. So here's our merge result will be like this. So these are the winners, and the lookup will be only two elements. One is removed one. Pretty easy. Yeah, and again, the code sample, how you can implement that. Basically, exactly what I said about grouping. Okay, so once we were kind of determined, we want to go that way. We have our modeled set. We started modeling the favorites API using our set. So exactly, we have the set of attributes that we want to synchronize, which is like a favorite data, right? Like name, location, whatever. And we have these three additional metadata fields, which are encapsulated by this favorite state element. This metadata is needed for synchronization. So one may ask, what do we do if we have equal timestamps? So as I said in the merge, we have these subgroups where we reduce. Okay, we have two equal timestamps for two elements. So as Nami said, CRDT has to guarantee has a guarantee to converge. So whatever happens, they have to converge to a winner in that case, in the reducing of the group. So if timestamp is the same, we continue comparing. So the next one, we check the removed flag. And in CRDTs, there is a term of bias, add or delete bias. So you can, depending on the business needs, you can say, okay, I prefer the deletions or removal, additions or removals, and etc. If even the removed flag is the same, we have to compare all the rest attributes. Even we have to have a deterministically deterministic converge operations, right? So even if we have to go to the real last attribute, we do the lexicographical order comparison because it's deterministic. So once we introduce these favorites CRDTs on all our layers, starting from the application, client application, server, database, as Nami said, everywhere we have the same flow, basically. Everywhere on each layer, we have this merge operation, which is applied to the values that coming from the other layers, right? So the update comes from UI, comes to the client merges to its local state. If something comes from the server, then this update can also blindly be merged to the local state. You don't have to worry that much about the conflict once you have your model implemented the right way. So for example, on the server, yeah, as Nami was explaining, the React case, for example, server is just sort of like a proxy. So server receives an update from the client, the diff. It fetches the data from the React, resolves the conflict, which is not shown here. And then it just needs to merge these values, the values from the database and from the client, and yeah, push to the database and return the resolved values to the client. That's it, pretty simple. It's pretty simple model to program because, well, yeah, basically you don't have to worry that much about implementing all this conflict resolution code on every single component separately, especially if you have, like, in our case, a zoo of different platforms, different clients that have to adhere to the same things. So far, probably you think like now, yeah, it's pretty good, pretty awesome. There are any problems with CRDT. Why don't we just start using CRDT, everybody, right? Like for all the kinds of applications. Why do we need just a normal set, normal data structures? Well, there are considerations and limitations that there is always a trick, right? So the first, I would say, problem, well-known problem with CRDTs is the growing Tomstones in CRDT set. So every time you delete an element, you produce this Tomstone, which is stored in the remove set, and intuitively, the more you perform updates on this set, you create more Tomstones, right? And potentially it's unbounded growth. So yeah, for example, we observed once we just rolled out our API, we observed that one of the beta user had only 5 non-deleted favorites. So in UI, he was seeing just a small piece of information that was synchronizing. But he was actually testing quite hard the platform, and he created like 3,000 deleted elements, which resulted in unzipped JSON like 1 megabyte. Wow, that's crazy. And imagine that it comes and goes via the wire. So yeah, we can argue, okay, we want to be able to prune the deleted elements. In the end, they don't bring us that much value to us. The question is when. So we can say that, okay, the requirement probably should be that all the clients has to observe that deleted element. Otherwise, it might be resurrected. So imagine that the client was offline, we just prune from a server, it goes back online, it sees that server doesn't have that value, tries to re-push back, server doesn't know that that element was removed, it adds it back. Not really good. So we started thinking, okay, how can we solve that? Well, first we thought, okay, maybe we can introduce some sort of client awareness. So each user has a set of devices associated with that account. We can say, okay, once we have the registration of these clients, and once we magically be able to determine the last synchronization time of the client, we can say, okay, if all the clients has synchronized, has observed that deleted favorite, we can prune it. It has some problems though. The first thing is that, well, the tracking the last synchronization time is pretty tricky. It proved to be tricky. And the second thing is that, yeah, it's depending on the time, basically. And we know what happens with time, right? So the next thing we started looking at was introducing some sort of time to live for Tomstones. So time to live, yeah, just a period of time after which the deleted the tombstone can be removed safely. The trick with that is that all clients and the server has to apply the same time to live rule. And again, it depends, of course, on the timing. So there can be periods of time of some sort of divergences. And of course, you have to manage properly these TTL rules. The next thing we were tackling on was optimizing the bandwidth. It's really important for our platform, as Nami said. So the classical way to work with our CRDT kind of data structures is that sending all the state. That's why actually they are called state-based CRDTs. So we wanted to optimize that. We wanted to say only diff on any updates. So in the example I show in the slides, actually the client has a set of elements. Server also has a set of elements. One, the B, has been modified. That's why it has this funky double quote. Client modifies also in the local state the two elements. And it sends it actually to the server. It can send only updated ones because, well, C is not changed. I think it's intuitive. Before, in the initial implementation, the server would actually do what? So it will merge the values, and then it will respond to the client in our REST API with the full merge set, which is not pretty effective if you have, for example, really big set with lots of tombstones, for example, and such. The one thing that we need to notice here is that server responds with the B, which was on the server before. So actually, the update for B from the client has lost. So we introduced this thing called scoped diff. So in the case of scoped diff, actually server responds with some values only in the case that these values actually were the winning ones, and server assumes that client hasn't seen them. So if all updates from the client have won, it will be the empty set in the response. But client doesn't really care. It just receives something from the server, it merges to a local state, the response from the server. That's it. So let's talk about the time. Yeah, there is problem with time. Well, there is no such thing as reliable time, right? And that's kind of a problem, especially if you have timestamps as the additional metadata for conflict resolving. So I like this quote actually from Jonas Banner in one of his presentations. He was arguing that actually tracking the time, when we track the time, we are not interested in the time itself. What we really need to do, at least what we really need in the distributed systems, is the ordering of the events. So we need to understand that what happened after what, some sort of like happens before relationship and etc. So in that case, yeah, the most important thing is causality and ordering. So we argue that actually time can be just good enough. But what does it mean? So let's look at two cases of ordering. One is ordering within a single node. Sounds pretty simple, right? It's there is no distributed state, just a single node. Well, it still can be tricky. So for example, I guess most of you know that if you're using JVM API system.currentMillis, it's not monotonic. There is no guarantee that if you call consecutively twice the system current millis, the second value will be guaranteedly higher than the first one, which might be kind of tricky if you are even updating locally your state of the same favorite. So for us, what is important, we use timestamp as a logical clock, and we need to have a guarantee that it grows monotonically. So we use on the client, for example, this +1 strategy. So what client does when it puts an update for the element in our set, so it needs to retrieve the timestamp, be it like a local provider of the timestamps, or it can be coming from a server, depending on the situation, if it's possible to fetch it from a server or not. But what it needs to guarantee that at least it won't be lower than the timestamp which is already in the set. That's why in the worst case we do this +1, which sounds a bit why, yeah? But actually, yeah, we just need to guarantee that this operation will win locally on a single node. So things become even worse when we talk about ordering updates from different nodes. That is really a tricky topic. So of course, we were kind of lucky. Some of our devices are PNDs, so they have this GPS clock. And if GPS clock is available, then you have a pretty precise timing. The problem is that it's not always available. So in the worst case, if we don't have this kind of, so if we don't have GPS clock, at least we prefer to use the server time over the client time. It's more stable. If we don't have even that one, well, okay, at least we fall back to this +1 strategy to preserve the updates on the local nodes. And here comes the edge case, of course. If you have multiple clients modifying the same element in the replicated set, and they don't have a reliable time by somehow, you might have edge cases. It's depending on the business requirements that it accepts that or not. Probably for financial transactions, not really. So let's talk about another problem. So we already seen that picture, merge everywhere. Awesome, yeah, we just have to use the same function everywhere. So one merge to rule them all. What's the problem? Well, the problem is that this merge has to behave the same way. So given the same input, it has to produce the same results. What if not? Well, divergence may lead to endless synchronization loops, which is pretty bad for the client, right? Of course, it won't corrupt the data on the server, but the client won't be usable, the particular client, because it will be always merging, producing the different values, and then pushing it back to the server, and back and forth, back and forth. We have some mechanism to actually protect us from the clients, the rogue clients, like rate limiting, etc. But still, it might be an issue. Okay, so what's the point actually? What we want to show? What did we want to show? That, well, sometimes the academia might be not that scary. I know that now we are at Lambda days. Most of you actually like have a pretty decent academic background, I'm pretty sure. But still, like for our mere pragmatic programmers, yeah, sometimes when we started looking, for example, at the CRDT, so we open the Wikipedia, right? And then you read that, what is CRDT? It's a bounded semi-lattice with join operation. Okay, what does it mean? And then there are lots of formulas and etc. So you have to spend some time on deciphering that stuff. But the point is that it's worth it sometimes. And some of these solutions are pretty neat. And it proved, in our case, be much better than some sort of homegrown, intuitively some homegrown algorithm that might not work in all the cases. Of course, there are still limitations, as we showed. And you have to understand the real usage of your system and constantly monitor and see if it still fits your requirements or not. And improving if it's needed. So speaking about the code, so we published the 2 small repositories with the samples that we showed for different CRDT sets, including the AllSet. The code is pretty small, actually. The AllSet implementation in Scala is like 80 lines of code. Well, it's not because it's Scala only. It's just because it's quite simple. And there is also a Java 8-based implementation if you're interested in. So here's our homework for curious minds. So if you're interested in some additional information on the topic, so the first talk actually was the one that inspired us to try out CRDT by Noel Welsh. I really recommend that talk. Also, Chris Michael John, formerly from Basho, he maintains a really, really nice readings list about CRDTs. The third one is a paper from the original authors of CRDT that coined that term, CRDT and strong eventual consistency. And these are 2 links, a bit more from the semi-practical side. So the last also work by Chris Michael John is a language based on Erlang, on top of Erlang, that has CRDTs as the sort of first-class citizens. It's really, really interesting stuff going on there. And also the Swarm.js, this is like a sort of a framework that makes use of CRDTs for synchronization, and in that link, actually, there is an example how that you can build the offline-ready web application. Okay, yeah, thank you very much.